A parabolic dam that is represented by the function x squared and reservoir's waterline is at 9 meters has what hydrostatic force acting on it? We will be assuming a density of water of 1,000 kilograms per meter cubed and a gravity of 9.81 meters per second per second. First step, we need to find the area that the water is pushing against on this dam. So here I have a graph of the water line, which is y equals 9, and a graph of the dam shape, which is x squared. Recall in calculus that we can find the area from the equation line to the x-axis. So we need to take the area of the water line of the graph, which is a rectangle, and subtract the area underneath the parabola dam to get the area that the water is pressing against on the dam surface. So we can integrate the y equals 9 equation and the x squared equation between the limits of 3 and negative 3. 3 and negative 3 are used because this is where the water line intersects the parabola from the dam. This can be found by setting the water line equal to the parabola equation. Using the constant rule and the power rule in calculus, we get 9x plus c minus x to the third divided by 3 plus c. The constant in this case will be a 0, but professors love to use a red pen, so I just wanted to mention it. So now if we plug in our limit values of 3 and negative 3 into this equation, we get an area of 36 meters squared for the area that the water is in contact with the dam. In a previous video, we determined that the equation for the moment about the x-axis is the integral of 1/2 the function squared. A moment is defined as a force times a distance to a pivot point, or moment arm. Plugging in our function of y equals 9 and y equals x squared into this equation and integrating, we get 1/2 9 squared times x plus c minus 1/2 x to the fifth over 5 plus c to the limit of 3 and negative 3 being equal to the moment. Plugging in our limit values, we get a moment of 194.4, which is going to be in the goofy units of meters cubed because we used a density of 1. Really, you can think in terms of the meters squared area of the dam is the force times the moment arm, which we are trying to solve for, which will be the point at which the average pressure is acting on the dam, is equal to the moment, which we just found in the previous step, which is 194.4 meters cubed. Really, it's meters squared times meters. Rearranging this equation to get what we're solving for, moment arm, to one side, we get that the moment divided by the area of the dam touching the water being equal to the moment arm of 5.4 meters. Going back to our graph, here is the point of 5.4 meters above the bottom of the dam graph. This is where the point of the average pressure acts on the dam. So if we take the water line minus the centroid we found, we get the depth below the water of 3.6 meters. Recall from the hydrostatic pressure videos that the hydrostatic pressure is the density of the fluid times gravity times the depth of the fluid. Also, here is a quick demo that demonstrates that as we go deeper, the pressure increases. Notice how the fluid flows farther out or has a higher velocity as the water gets deeper. Plugging in our values, we get a hydrostatic pressure of 35,316 pascals, or newtons per meter squared. If we take the average pressure acting on the dam times the surface area being touched by the water, we get a hydrostatic force acting on the dam of 1,271,376 newtons. Poll update. That concludes this video. Hope that I've earned a like, share, or subscription. If you enjoyed this video, you may enjoy one of these videos as well. Let me know how I'm doing in the comments down below. Thank you for watching.